Hello everyone, welcome to Basics e-learning. In lesson 4 video, I am going to discuss basic discrete time signals, their nature and also few examples on those signals. And the basic discrete time signals that I am going to discuss in my video are unit step sequence, impulse sequence, ramp sequence, exponential function, sinusoidal function, exponentially damped sinusoidal function, and also pulse function. The first signal in basic discrete time signals is step function. Step function is represented with u of n. Unlike your discrete continuous step function, here the time scale, instead of time scale, here you are writing it as n. It is indicating the discrete time scale, unlike your continuous time scale. And this u of n, your unit step function, is defined as 1 for n greater than or equal to 0 and is equal to 0 for n less than 0. As this is a discrete function, the amplitude is also defined at particular intervals, that is at discrete intervals. That is, suppose here n is equal to 0, 1, n is equal to 1, again amplitude is 1, at 2. So the signal is defined only at instants at n is equal to 0, 1, 2, 3, 4. Again the amplitude of these signals at these instants is unity. Everywhere it is 1. See here, you can see this in the picture. Now suppose if n is less than 0, then what happens? Again the amplitude is 0. Here also it is defined at particular intervals only. N is equal to -1, -2, -3, -4. Everywhere you have amplitude as 0 only, but defined at only particular intervals. See this, n is -1 means amplitude is 0. N is -2 means amplitude is 0. So this is how they have defined this discrete time step function. And the next function here is unit impulse function. So this is also defined like as in your continuous time signals. Continuous time signal is defined as delta of t. Here discrete impulse function is represented with del of n and it is defined as del of n is equal to 1 for n is equal to 0 and is equal to 0 elsewhere. So at discrete instants of time, as they have marked in the picture here, at n is equal to 0, that is here, n is equal to 0, only you have an amplitude of 1. It is the impulse. It's a spike at n is equal to 0. Elsewhere, the amplitude is 0, right? So at n is equal to 0, you have an amplitude of 1. Elsewhere, the amplitude of del of n, that is your impulse function, is 0. See here at n is equal to 1, 2, 3, everywhere it is 0 till infinity. Similarly, on the negative side, -1, -2, -3 till minus infinity, you have 0 amplitude for your impulse function. The amplitude of the impulse function exists only at n is equal to 0. As we are defining for unit impulse function, the amplitude of del of n at n is equal to 0 is 1 or unity. Now let us discuss the important properties of this impulse function. The first one is product property. Suppose if you multiply a signal, any discrete time signal, with this discrete impulse function, then what happens to that signal we'll see. Suppose let us define a signal x of n, right? So take x of n as you wish, as a sequence of numbers. So here I am taking -1, 2, 4, -3, right? So I am taking my n is equal to 0 here. Wherever you are marking arrow here, that is nothing but this is the amplitude of n is equal to 0 place. Then towards your left side, this is n is equal to -1 amplitude. This is n is equal to +1 and +2. Towards your right side, you have to take positive n, and towards your left side from the marking, you have to take it as negative scale. So if you try to draw this x of n versus n, so this is 0, 1, 2, 3, -1, -2, right? So at n is equal to 0, I have amplitude as 2. So let us mark this one. Then at n is equal to -1, as I am moving towards my left side, the amplitude is -1. So at -1, I have my amplitude is -1. So Minus 1 means towards the negative side, right? So that is negative y-axis you have to consider. Then at n is equal to 1, I have my amplitude as 4. So somewhere I'll mark here. Right. Next, at n is equal to 2, the amplitude is minus 3. So put it down. This is minus 3 amplitude. Right. So this is my x of n. If you multiply this type of x of n with your regular basic unit impulse function, discrete function, what happens we'll see. So what is del of n? Del of n is equal to 1 only at n is equal to 0. Elsewhere it has 0 amplitude. Now what happens? Just multiply the amplitudes of x of n with del of n amplitude at each and every instant. So at n is equal to minus 1, I have amplitude as minus 1. At n is equal to minus 1, what is the amplitude of del of n? It is 0. Yes. So minus 1 multiplied by 0 is 0. So I'll try to write down the signal here, x of n multiplied by del of n. So at n is equal to minus 1, I have amplitude 0. At n is equal to 0, here I have the amplitude as 2. Then for del of n it is 1. So multiply. At n is equal to 0, I am multiplying the two amplitudes. 2 into 1 is 2. Mark this one. Next, at n is equal to 1, x of n amplitude is 4. But del of n amplitude is 0. So the amplitude at n is equal to 1 for the resultant signal is 0. Then at n is equal to 2, I have my amplitude as minus 3. But for del of n it is 0. So the resultant signal, the amplitude at n is equal to 2 is 0. So this is your resultant signal. So the property here is defined as x of n multiplied by del of n is nothing but x of 0. What is x of 0? The amplitude of the signal x of n at n is equal to 0 is only the resultant signal, isn't it? See here, this is x of n. The amplitude of the signal at n is equal to 0 is how much? 2. So this impulse or this instant is represented as x of 0. X of 0 is nothing but amplitude of x of n at n is equal to 0. Suppose you want to indicate this one, then you will write it as x of minus 1. This 4 is nothing but x of 1. This minus 1 is nothing but x of 2. Means amplitude of x of n at n is equal to 2 is minus 3. Right? So the resultant here is x of 0. So this is the product property of your impulse function. The next property here is shifting property. So let us see what is this shifting property defining. Shifting property is defined as x of n multiplied by del of n minus k is equal to x of k. What is this del of n minus k? The shifted version of your del of n by k units. So let us take one example and then I'll explain the property here. Suppose consider x of n as a sequence of values here. So 0, 2, 4, 3, something I'm taking some 1, right? So my n is equal to 0 I'm marking here. So towards my left side this is n is equal to minus 1 and minus 2. This is plus 1 and plus 2. So let us indicate this on the picture. This is x of n and I'm marking this as n. So what happens? At n is equal to minus 2 I have amplitude as 0. At n is equal to minus 1 I have amplitude as 2. At n is equal to 0 my amplitude is 4 here. And at n is equal to 1, 3, right? Then at n is equal to 2 we have an amplitude as 1, right? Now I have to take this shifted version of del of n. So what is del of n defined? Is equal to 0 for n is equal to 0 and is equal to, sorry, it is equal to 1 at n is equal to 0 and is equal to 0 when n is not equal to 0, right? So del of n is equal to 1 at n is equal to 0. Now I will consider some shift on this signal. Just I am shifting this on the scale here either to the right hand side or to the left hand side, n minus 3. So what happens here? Del of n minus 3 is equal to also 1 when here you are defined for n is equal to 0. Now instead of n I have n minus 3. You write it. N minus 3 is equal to 0 means at n is equal to 3. So at only del of n minus 3 is equal to 1 only at n is equal to 3. Elsewhere it is 0. You understood, right? Del of n is equal to 1 at n is equal to 0. What happens to your del of n minus 3? Del of n minus 3 is also equal to 1, but instead of n we have n minus 3 here. So you make it n minus 3 equal to 0 means at n is equal to 3. That is, the same del of n is shifted to n is equal to 3 with amplitude 1. Just move towards your right side on the scale. Now, you just multiply such type of signal, that is del of n minus 3, with your taken x of n in your example. So, this is 3 suppose say. So, the value here is 1. Elsewhere you have 0 amplitude, even in the negative side. Now, you just multiply. What happens? We'll see. This is minus 1, minus 2. Amplitude is 0. So, you just multiply each and every instant of x of n with each and every instance of the shifted version of your impulse function. So, at n is equal to minus 2, the amplitude of x of n is 0. Here, del of n minus 3 also it is 0 at n is equal to minus 2. So, the resultant amplitude is 0 at n is equal to minus 2. Then minus 1, 0, 1, 2, 3 we'll see. Okay. So, what happened to the signal here? At n is equal to minus 1, this is you have amplitude 2 multiplied by 0. So, anyhow 0. At 0, you have amplitude of 4 for x of n, and here it is 0 because it is shifted, no? So, again here also it is 0. This is my resultant signal. Okay, x of n multiplied by del of n minus 3. At n is equal to 0, I have 0. Then at n is equal to 1, here you have amplitude 3 multiplied by here 0. Right? So, that is 0. Then at n is equal to 2, you have 0. Here n is equal to 2, you have 1. So, 1 multiplied by 0, 0. At n is equal to 3, x of n itself is not defined. So, the value is 0. 0 multiplied by 1 is 0. So, it is 0. Right? The signal is not existing here if you are multiplying with the shifted version, because you don't have any impulse at n is equal to 3 here. So, what is your amplitude of x of n at n is equal to 3? 0. So, that is what you are getting at x of k. Right? That is nothing but if you are multiplying this signal, x of n multiplied by del of n minus 3, that is nothing but x of 3, which is nothing but 0. Suppose say you are multiplying this with del of n minus 2. What happens here? Instead of 3, you write it 2. Now what happens? 1 into 1. That is x of n at n is equal to 2. The amplitude is 1 here. Del of n minus 2. The amplitude is 1 at n is equal to 2. Now you multiply. 1 into 1 is 1 you will get in the resultant signal. Now what happens here? So del of n multiplied by del of n minus 2. X of n multiplied by del of n minus 2 is nothing but x of 2. What is your x of 2? 1. Amplitude of x of n at n is equal to 2 is 1. So that is your shifting property on impulse function on any given signal. And the next signal here is discrete time exponential signal. This exponential time signal is defined as x of n is equal to a into alpha per n. Let us see how the signal will be. So now suppose say n is equal to 0. That means x of n is equal to a into alpha per 0. So anything per 0 is 1. So this is nothing but a. So irrespective of whatever it may be the value of alpha here, for x of n when n is equal to 0, you have an amplitude of a. See here in the first picture, at n is equal to 0, you have an amplitude of a. Again in the second picture also, at n is equal to 0, you have an amplitude of a here. So one is exponentially decaying curve and the other one is exponentially increasing curve. Let us see. Now suppose say alpha is between 0 and 1. So that is alpha is between 0 and 1 means what? Here it should not be 0. There is no equal to here, right? So alpha should be greater than 0 and less than or equal to 1. Suppose take some value, suppose say some 0.5. Okay, alpha is equal to 0.5. Then what happens we'll see. at n is equal to 1, suppose say you're taking for n is equal to 1. So 0.5 whole power 1, right? Alpha is equal to 0.5 and n is equal to 1. Then what happens? 0.5 times a. So a value is reduced from the exponential signal amplitude at n is equal to 0 is a. At n is equal to 1, it reduced to 0.5 a. When alpha you are taking it as 0.5, that is less than 1. Now suppose take n is equal to 2, then what happens? N is equal to 2 a into 0.5 whole square, right? 0.5 whole square means 0.25 a. So again from 0.5 to 0.25 it is reduced. So it will be keep on reducing, right? So that's why if you are selecting alpha between 0 to 1, then the curve will be exponentially decreasing in amplitudes, right? So this is your discrete time exponentially decreasing curve. Suppose if you're taking alpha is greater than 1, so take some alpha is equal to 2, then what happens? X of 1 is a into alpha per n, no? So that is 2 per 1, so 2a. So from a it is raised to 2a. Then suppose you are taking n is equal to 2, a into 2 per 2, so it is increased to 4a. So a, 2a, 4a, the amplitudes are keep on increasing when you are taking alpha is greater than 1. See here, this will indicate you exponentially increasing curve, right? So this is all about exponentially decreasing curve and exponentially increasing discrete exponential curves. The next signal is discrete time sinusoidal signal. Discrete time version of a sinusoidal signal is defined as x of n is equal to a cos of omega naught n plus phi. In continuous time signal, omega is represented like this, w. Here it is, the symbol is like this, omega or omega naught. Here a represents the maximum amplitude that is taken by the signal x of n. Omega naught is the angular frequency and phi is your phase angle. Here n is a dimensionless quantity, no units here for n, it's a number, right? So and omega naught and phi are measured in radians. Unlike any continuous time signal, here discrete time sinusoidal signals are not periodic for any arbitrary value. I think you might have remembered x of t is equal to a cos of omega naught t plus phi, right? So here omega naught can be any value such that this x of t is periodic. But here omega naught, here in this case in discrete time signal, omega naught cannot take any value to make x of n as periodic. Here the condition is omega naught should be equal to 2 pi into m by n. So omega naught must be a rational multiple of 2 pi. Omega naught should be a rational multiple of 2 pi. Then only I can say x of n is a periodic signal. Here this is the condition. This is very important in problems also. So this is the condition for the sinusoidal signal to be periodic, where m and n are any integers. So m and n are any integers, right? So omega naught should be a multiple of 2 pi. Now let us consider one example. Suppose say x of n, I am taking cos of pi by pi n pi by 4, right? Pi by 4n something, right? So now you have to compare this with the standard form, that is a cos omega naught n plus phi. So here if you compare, a is equal to 1 here amplitude, then omega naught is equal to pi by 4, then phi phase angle is 0, right? Now this omega naught is pi by 4, this you have to write it in this form, multiple of 2 pi. So to write it in the form of multiple of 2 pi, I will just multiply both numerator and denominator with 2, then it will be 2 pi by 8. So that is nothing but 2 pi into 1 by 8. So if I compare this with the condition, I have 2 pi into m by n, that is nothing but 2 pi into 1 by 8. For me m is equal to 1 and capital N is equal to 8. So this is the periodicity of the signal, n is equal to 8. Right? So the fundamental period of this continuous discrete time sinusoidal signal for this pi n by 4, it is equal to n is equal to 8. Suppose say if it is not the multiple of 2 pi, then you can't say the given discrete time sinusoidal signal is periodic. The next signal is exponentially damped sinusoidal signal. The discrete version of exponentially damped sinusoidal signal is described as x of n is equal to b r per n sine of omega n plus phi. So again here also it is a combination of an exponential signal and a sinusoidal signal. Damped means as the time increases, the amplitude of the signal has to reduce. So let us see this with one example. So here, to make the amplitude decreased along with the time, as the time increases, the condition is value of r should be between 0 and 1. So let us consider some values. Here b is the amplitude of the signal x of n. So I am taking b as some 5. As my r value has to lie between 0 and 1, I am taking r is equal to 0.1. And this omega is the frequency that I am taking it as pi by 2, angular frequency. Then the phase angle I am taking it as 0. Now we'll see as the time value, that is the n value increases, the discrete time signal value n increases, then what happens to your amplitude of x of n. So let us consider first case x of n is equal to 1, then x of n value. So just substitute all these values in this standard form. Value of b is 5, r I am taking it as 0.1 and n is 1, so 0.1 whole per n. Sine of omega n plus 5. What is omega? We have taken it as pi by 2 into n is 1, anyhow phi value is 0. So sine pi by 2 means sine 90 degrees, it is 1. 5 into 0.1 into 1, right? So that is 5 into 0.1 into 1. I am taking it as, now this is 0.5, right? Now take n is equal to 2. Now the time has increased to the second value, right? So x of n is equal to 5 into 0.1 whole square into sine of pi by 2 into 2. So this is sine pi. So sine 180 degrees, that is 0. So 5 multiplied by 0.1 whole square means 0.01 into anyhow 0. So the value is 0, right? Suppose if you take n is equal to 3, then what happens? X of n is equal to 5.1 whole cube into sine pi by 2 into 3. Then what happens here? 3 pi by 2. So it is minus 1. So 5 into 0.001 into, what is the value here? 1. Sine 3 pi by 2, it is 1. Right now, what is the value you are getting? It is 0.005. So as you observe here, if the n value is keep on increasing, right, the amplitude of x of n is keep on decreasing from 0.5 to 0, 0 to 0.005. So eventually the value turns to 0. The amplitude of the value, the amplitude of the x of n reaches 0 as the n value tends to infinity. The last signal in basic discrete time signals is pulse signal. So again here also, like in continuous time signals, pulse signals are of two types I have explained. One is the rectangular pulse and the other one is triangular pulse. So the rectangular pulse is defined like this. Rectangular of pi by 2n is equal to 1 for mod n less than or equal to capital N and is equal to 0 elsewhere. That is here, this 2n in the denominator is indicating the range of the signal. So in that particular range you have an amplitude of 1. Elsewhere it is 0. Suppose say the signal that you need is from -3 to 3. So totally 2n plus 1 pulses it will come, right? So here 3 to -3 minus n to n, no? That is 3 plus 3 is 6 plus 1. This 1 pulse is at the 0 impulse, right? At time n is equal to 0 here you have, right? So now you have the pulse will be like this. So you have an amplitude of 1 at 1, 2, 3 extended, and similarly at -1, -2, -3, right? So that with amplitude 1. Elsewhere you have 0. So this type of pulse we call it as a rectangular pulse. Similarly, triangular pulse is defined like this. Triangular of n by capital N is equal to 1 minus mod n divided by capital N where mod n should be less than or equal to n. Otherwise, it is 0. So this is nothing but here the amplitude has to decrease from 1. Gradually it has to decrease. Suppose you keep here n is equal to 0. Small n is equal to 0. It is indicating the time scale, no? Here small n. So if the small n is 0, what happens? This part will be vanished. So the triangular pulse has an amplitude of 1 at n is equal to 0. Then if slowly n value increases, then what happens? The amplitude is reduced from 1. Suppose say I am taking capital N, that is the range as 2. Okay. Now n is equal to 1 means what? At a time n is equal to 1 means the amplitude of the triangular pulse is 1 minus, in place of n I am writing 1 divided by 2. So next pulse amplitude will be half. Then next pulse, n is equal to 2, you write 1 minus 1, 0. So like that it will be keep on decreasing. The amplitude decreases slowly to 0 when n is equal to n. When small n is equal to capital N, then the amplitude of the triangular pulse reaches to 0. So again here also for this triangular pulse, the number of the pulses are 2n plus 1 and the range is minus n to n. For more videos, please do like, share, subscribe to our channel. Let us know your suggestions and queries in the comment box. Thank you.